So, I hope I'm audible. So, sorry for the interruption. So, I was here I was explaining about the different types of appendages type. So, there are four types of appendages like bar feeding, bar feeding plate, plate feeding bar, plate feeding plate, and then the bar feeding bar. And then the definitions and other thing I have already discussed. So, like I was giving an example so this is also called as I was giving an example where there was a plate which is also called as a parent part. Okay, so and then this is connected by a bar. So as you can see, like from the definition, the bar has length or width is less than 3 to 4 times the thickness. Okay, and then this is also called as a parasite because as a parasite sits on some some humans or other parts. This is the same way it is like treated like as a bar is sitting on a parent part. So this is a example of a uh, this is example of a bar feeding plate. So now another example I can give you as like this is a bar, and then it is feeding a plate. So as you can see, the length and width is higher than this thickness. So this will behave as a the above one is a this one is a bar, and then the this is the and this is your plate. So the so the thing is why I'm discussing is that like sometimes in your exam the problems may come one second. Sometimes in your exam the problems may be there might be given uh, we need to design a riser while but the cast has sometimes of protrusion this one, the first problem we will be doing today. So as you can see, there is a plate of dimension 25 by 12.5 by 5, and then there is a bar also. So this is the example of first type, which is our bar feeding on plate. So this is called bar feeding on plate. Is that because first your riser will fill the plate, then the bar will get filled. Okay, so the bar has dimension 10 by 2.5 by 2.5, while the plate's dimension have already been given. So we need to find the volume of a riser. So the procedure is firstly, if you see the volume of the casting, firstly okay, one second. So here first we will assume that there is no bar. Okay, so if we will assume this, if there is no bar, our casting has the volume as it will be as a cuboid. So we can directly find our volume. So in the figure, the dimensions are not given, so I'm assuming it is in centimeter. So firstly, we will calculate the dimension or the volume of the plate. So it will come as around 1562.5 centimeter cube. So once your volume comes from the NRL method, like the problems we discussed in the previously in the previous tutorials, we calculate the shape factor. So which is basically the ratio of the length and width and uh, the sum of your length plus width divided by your thickness. So similarly here we will calculate here the shape factor. So your shape factor will come as okay, so your shape factor will come as your length is 25. From here you can see like the bigger dimension is 25, so your shape factor will be 25 plus 12.5 divided by your thickness is 5. So your shape factor will come around 7.5. Now here like you need to see in your exam if your problem comes, then from here like your NRL you need to go to the your NRL curve to find out the there will be some curve or a table will be given. From that you need to calculate the ratio of your volume of the riser divided by volume of the casting. So from here like so I have already calculated like your volume of the riser and volume of the casting for this particular shape factor of 7.5. It is 0.575. Okay, so from here now your volume of the casting you already know, like assuming no bar, there is no bar. So from here like you can calculate your volume of the riser as 0.575 multiplying by the volume of the casting is 1562.5. Right, so this will come as around 62.5 centimeter cube. So once you like calculated now, sorry, I think I did something wrong. Okay, so you have your volume of the riser divided by volume of the casting as 0.575. So now you can calculate your one second. The volume is, this volume will be like 894. This volume will be around 894 centimeter cube. Okay, so it will be around 894 centimeter cube. Okay, so now after this we will focus on this appendage or bar. After like doing this part, we will focus on this part. Okay, so firstly we assume that there is no bar. Okay, so from that we found the volume of the riser as 894 centimeter cube. Now we will find the volume of the appendage or this bar. So volume of this appendage will be, as it also behave as a cuboid, so we will multiplying as 10 into 2.5 into 2.5. So this will come as 62.5 centimeter cube. Okay, so from here like after this we will calculate the ratio of your thicknesses for your the parasite part, which is the bar part, and then this is your the plate part. So this will be your parasite part. I'm writing in short form TP, and then this will be your parent part, which is your plate part. So this will be coming as like the thickness is 2.5 here. This thickness is 2.5, and here the thickness is your 5. 2.5 divided by 5, it will be around 1 by 2, 0.5. So after like after finding the ratio or the thickness, we will go to again the NRL curve. So we will go to this curve. Like from here you can see like there are bar feeding plate, plate feeding bar, and bar feeding bar or plate feeding bar curves. Three curves are given. So you will go to the plate feeding bar. So this is your plate feeding bar, and then around 0.5 or 0.5 thickness of the parasite to the thickness of the parent ratio is 0.5. So you will go to the 0.5 and then go to the upside. Then from here you can calculate that the percentage of parasite volume. This curve, if it will come in exam, this curve will be given. So from here, you can see uh, the volume of the riser is around. So if you see, like if I go to 0.5, okay. So you can see like that the volume of the riser is around 30% of your appendage. I think someone wants to. Okay. So here, after going through the figure or curve, you can see. So you can see volume. Your volume of the riser will be 0.3 times your volume of the appendage. Like the volume we have already like this volume we have already calculated is coming as 62.5. So from here we will be getting your volume of the riser as this will come as 18.75. Okay, and 18.75 centimeter cube. So your total volume of the riser which you would need to fill is will be the sum of this and your this one which we calculated. Okay, so that I can write as VR final your total will be volume of your appendage plus volume of the riser which we calculated. I will say it as A and B. So if I say it A, if I say it B, then your sum will come around. So this will be 894 plus 18.75. So this will come as around 913 centimeters. Okay, and once you calculate the volume of the riser, if you will write it as like if in question instead of volume of the riser the diameter was asked, then you could have easily substituted this volume to the pi by 4 d cube. I'm assuming that uh, h and d are same, so you can easily calculate the diameter. So for once I will again revise this problem, then we will move to the second problem. So in this problem, like there is a plate on which there is a bar is given. So we need to calculate the volume of the riser. You can see so whatever whenever this type of problems are given in the exam, firstly we will assume that there is no bar and or system is feeding without the bar. So we will assume that there is no bar and then we'll calculate the volume of the casting. So from here, like you can see, like the volume of the casting is LBH as it is a cuboid. So your volume will be 25 multiplying by 12.5 multiplying by 5. So for this we calculated the volume. Now from the NRL method we like we solved in the previous tutorial. We find your shape factor. The shape factor is the ratio of your length plus width divided by the thickness. So your length is 25, your width is 12.5 divided by your thickness is 5. So we calculated the shape factor. Now from the shape factor values, we will go to the NRL curve to calculate the ratio of the volume of the riser to the volume of the casting, which comes as 0.575. From here, we will calculate the volume of the riser if there is no bar. So the volume of the riser will be 0.575 multiplying by the volume of the casting, which is when there is no bar. So this volume comes around 894 centimeter cube. You can cross check it. So after that, once we calculate the volume of the riser when there is no bar. We will go and see again, go calculate the, sorry, and then we will calculate the volume of a bar. So your length is 10, width is 2.5, and then your thickness is also 2.5. So we'll calculate the volume of this appendage or volume of this bar. This will come around 62.5. After that, like from the NRL, there is one curve, like which is plotted between the percentage of parasite volume to the thickness of parasite to the thickness of the parent. So we calculated the thickness of your, the ratio of your thicknesses. So which is your thickness of the plate is 2.5. This is 2.5 divided by your this thickness, which is around like 5. So we calculated this ratio, which comes around 1 by 2. So and then we, after that, from this we will go here 0.5, and then we will find that there is the percentage of the parasite volume is 30%, approximately 30%. This is not, I just taken to explain you. It may be 31, 32 as per your convenience. You can go and go to this curve and then see. So from here, like finally we need to sum the two volumes to calculate the total volume of the riser needed. So the, we can say like I will write what is, there is a rule of thumb, like which will feed which one. Firstly, so this I will write it as like your rule of thumb is your thicker will feed the thinner one. This is the rule of thumb for solving this type of problem. Okay, so your thicker will feed the thinner one. So like thicker here is the feeder and the thinner will be the feed. So thicker is your feeder, like which will feed something, and your thinner will be the feed which will get filled up. So here you can see like your thicker is, which one is more thicker? Definitely this thickness is of the plate is 5, and then your thinner is this one, whose thickness is 2.5. So this will feed this. So now in exam, if this thickness was higher, you could have like done a mistake. So you need to go very carefully while solving these type of problems. So this is the rule of thumb to solve these kind of problems. So now after that I will move to the second problem. So as you can see, so volume of the riser, we need to calculate the volume of the riser for this problem. So this is a complex problem. So as you can see, like in the middle part, there is the dimensions are 140 by 45, and then the length is 175, and then there are like two outer casings of dimension 215, 100, and 25. So I request all of you to please try to solve this problem, and then we will move to the another problem, and then after that the theory part. Okay. So here you, firstly you will assume it as here also there are holes. These two are identical. I forgot to draw them. This hole is also present here and here. So there are this hole, this hole. There are two holes, and there are two holes here. Okay, so try to like see, or I want to see your approach, like how you will be solving this. If you know the approach, you can easily solve this. Yeah. So anyone who like would like to share like or tell like how we can approach or we can solve this problem. So firstly, we need to see which one is the appendage one and which one will be your like normal plate. So firstly, we will calculate the volume of both these, this outer part and this and the inner part. So if we will calculate the volume of this inner part, it will be like we need to do a lot of assumption in this kind of problem because we can't calculate the exact volume. Firstly, I'm assuming it is a cuboid. So firstly, this from here the volume will be like around 1102500 centimeter cube for the central part. Now, if I will see these side ones. So firstly, this volume will be like 215 into 25 multiplying by 100. So this volume will be like 537,500. Clearly, the volume is less. So this will be the feeder, and then this will be your feed, and this will be your feeder. And one more thing is that like where we put the riser in the thickest part uh, of your casting. So we will put your riser at this part here. Okay, because this is the thickest, like 45, and this is only 25. So we will put your riser here. This will be your riser. Okay, so now put riser. Okay, so now we will calculate again the shape factor. Firstly, we have already calculated the volume. Now we will calculate the shape factor. So your shape factor will be like your 140 plus 175 divided by your 45 thickness. This will come as 7. So now you will go and they will in exam there will be some table or curve will be given like for from which for the particular shape factor which is 7 in this case you can go and find out your ratio volume of the riser to the volume of the casting. So for this value your volume of the riser to the volume of the casting is 0.5. Okay, so so this from this you will find your volume of the riser as zero point 0.5 of this. I'm directly writing here, so it will come as 551250 centimeter cube. So this will be your volume of the riser. And here like two appendages are given. One is this and one is this. Now for this, the volume has already been calculated. So the total volume of this appendages will be twice of this, so which will be 105,000. Sorry. So now this is a case of plate feeding plate because the thickness of both of them are like considerable. So this is your case of plate feeding plate. Okay, this is not your case of like plate feeding bar or something. This is your case of plate feeding plate. This you need to like see carefully. Firstly, you need to know how classification between the plate and bar can be done, and after that you should be sure which one where you should be placing a riser or this, and then after that you should be able to see or like see from the curve of the NRL method like what will be the ratio of the volume of the riser to the volume of the casting for calculating the volume of the riser without appendages. And then secondly you need to be sure uh, you need to see your curve carefully in the second case which will be the ratio of these two parts. So again like will be like So after that you need to, after that you will calculate the ratio of these two parts. So ratio of your appendage part and then ratio of the thickness of this outer part. So this will be coming as like as you can see, like here the thickness is 25 and in the below part it is 45. So the ratio will be 25 by 45. So this will come around 0.555. Okay, from here like you again need to go to this curve. Okay, so the ratio was 25 by 45. So from here again, this was your case of plate feeding plate. You need to see this line. Okay, so when this ratio will come around, I have already written. So from there, this is your value will be coming around 0.55. This will be your value. So now you from this you can calculate. This is not the ratio value. This is the ratio from the curve. Okay, so now from that you can calculate the parasite volume of the parasite. Okay, so which will come around 0.55 multiplying by your volume of these appendages. Then the volume of these appendages is your 537500 multiplying by 2 because there are two appendages. So your final volume of the parasite from here it will be coming as 596675 centimeter cube. So now again you can calculate the total volume of this plus volume of this. So you can so the total volume will be the sum of these two volumes which I have calculated. And then if your diameter is given, you can calculate the diameter by equating this to pi by 4 dk. So I am not calculating the thing, but I wanted to convey the message of like how the problem will be solved for this type, or like what is the procedure of these. So there we have already did two problems. So if anyone has any doubt till now in these two problems, please tell me. We'll discuss this, and after that there will be one last problem, and then the week 5 and week 6 problem will be wrapped up. And from after that we will be discussing about the number of risers or riser design. Okay, so if anyone has any problem till now, like in the week 5th problem or week 6th problem till now, please feel free to discuss. So this sometimes this problem is a tricky one, so that's why I'm saying if anyone has any issue like any problem, please ask. Okay, then if no one has any doubt, like so till now like we have discussed about this last problems of this NRL method, and then so now we will move to the third problem of this. This will be the last problem of our complete session. After that, in the next section, we will be discussing about the next week's like week 7's problem. But after this problem, we will be briefly discussing about the riser design. Okay. Okay, then so this is your problem. This problem which we need to like solve from the Keynes method. So there is one side riser is here. This one is your side riser, and then this is your like slab which we need to fill. So from the Keynes method, we already know x is equal to a divided by y minus b plus c. And in problem, your a, b, and c value are given here. So you need to calculate the dia of your riser. So please try to solve this because one problem we did in the last week from this Keynes method section, and then this is the last problem which we will discuss. So please take your time, 1 or 2 minutes, then we will discussing this. So okay, then if anyone try to solve this, or can anyone like tell me the approach, like how it will be solved? So here from the Keynes method, we already know like this is the equation of the Keynes method, and there is one more term for the y term, which is the ratio of the volume of the riser to the volume of the casting. Okay, so from this, uh, volume of the riser is so volume of the riser will be pi by 4 d cube, and assuming that h is equal to d, and here so from here I can calculate the volume of the riser as diameter is in terms of diameter I'm writing it as 0.25 pi d cube. Okay, it's not a big thing. Now I will be finding the y part, which is the ratio of the volume of the riser divided by the volume of the casting. So it will come as around 0.25 pi d cube divided by the volume of the casting. The volume of the casting is will be 25 by 25 by 5. So this will come around 3125 centimeter cube. So this will be a y part. So from here you can calculate your y as 0.000215 d cube. Okay, so now after this, so after calculating the y, I will be calculating the x part, or so the x part can be written as, which is your freezing ratio also, which we have already discussed in the theory also as well as in the tutorial. So your x is the ratio of the a by v of the casting and your riser. Okay, so from here it will be coming as your area of, or the cast area is 1750. Okay, so this will be calculated as 2 into LB plus BH plus HL. Okay, so your area of the casting is 1750 and your volume of the casting will be 3125. Volume is 25 by 25 by 5 as it is a cube. One second. अनिल अनिल वो हिल गया तार इसका डिस्चार्ज हो रहा है देखो ना थोड़ा अनम्यूट करो. Okay then, so from here you will okay then area of the riser, or you can put it as firstly I'm writing it as area of the riser only, then I will in your volume of the riser you have already calculated as 0.25 pi d cube. I am doing this because I am I want to write it in terms of diameter. Then there will be then I will put these x and y in the values in the equation of the Keynes method, and then I will sort it, and then I will make a linear type of, I will try to make a linear type of equation in terms of diameter only, then I will find out the diameter. Okay, so and here from here your area of the riser will be pi dh plus pi by 4 d square, as it is a side riser, so we need to consider this. And we have already discussed like uh, the how we take this area of the riser in terms of side riser and top riser. You can watch the previous tutorial for your further clarification. So this will be like area will be like pi d square as d is equal to h is given. So pi d square plus pi by 4 d square. So this will come as like around pi by 4 pi d square. So this will be your area of the riser. Okay. So we will put it here now. So write x in terms of d. So if you will sort it like so if you will like do the calculation, you will find out your x is 0.112 d. So you can all easily simplify this by putting the value. I'm not doing this. Now I will be putting this is in the equation of the Keynes method, which is this: x is equal to a upon y minus b plus c. Your x is given like 0.112 d, and then your a upon a is like zero point 0.1 given. Y we calculated this 0.30251 d cube minus 0.03 plus 1. Now you need to simplify this equation and then you will get a linear equation. So you will get this equation: d to the power 4 minus 8.93 d cube minus 119.5 d minus 2490. Can anyone tell me like how we will solve this equation if this type of problem comes in your exam? Like how we will solve this example? How we will like find out the diameter? One method is like easily you can like go do from the your scientific calculator. By putting this, you can calculate the roots of that equation. Another, if there is any other method, like anyone knows how to solve this kind of equation. So simply like if in exam it came and you don't know the values, like Kelsey is not given like for like power to the power 4, like advanced scientific calculator, if they are not given, then what you need to do is like you will simplify this equation by putting random values of d. Like if I put 1, 2, 3, 4, 2, again higher values, you will see like what are the roots coming. Like if you first you find if the value is coming positive or negative, and if you see like at what point the change was from positive to negative, the change in the value of the roots, and just see like if there is if you find the nearest value, like after which the signs are changing, you can like calculate the value of d by approximation. Or besides this, you can do from Newton-Raphson method and other methods also, which you might have like studied in your like advanced mathematics courses. So okay then, this was the last problem of the week 5th and week 6th, which I wanted to cover. So anyone, if anyone has any doubt till now, we will discuss, or we will go to the theoretical part which I wanted to cover. Okay. Anyone who has any doubt? Okay then, we will move to the uh, next part then. So which is the feeding distance in, or like basically the feeding distance for different things, like so this one is your riser, this one is your riser. So we need to calculate at around what thickness or at what distance this riser will feed your cast. So firstly, like feeding distance in steel plates is given, like so these like values, like how these came, like these are came after a lot of experimentations, and these are like we can say like generally people reported that. So it is an average of a lot of things. So for the feeding distance in steel plates, you can see here, this is your riser part. The plate has a thickness of T. Then the riser can feed at a maximum distance of 4.5 T to the left and 4.5 T to the right part. And from here, the it is assumed that here your edge is here. So the riser generally contributes 2T only, and 2.5 T is contributed from your edge contribution, because from edge also like solidification will come. So a riser can feed a maximum of like 2T distance to the left and right part. So as per this will be like helpful in your this will be helpful in your problems if like in exam it comes like till what distance your this riser will be feeding. So after that, you can see from this figure, the length greater than the maximum distance. So if your riser is feeding more than so the riser can feed only 2T distance, but if there is like one provision, then the like center line shrinkage will come here. Okay, so and from here the shrinkage will come here, and your casting will not be properly made. So there might be a lot of defects also. So that's why we need to properly design your risers. So you can see from here the riser will fill 2T distance, and from your edge it will be filled by 2.5 distance, 2.5 T. Okay then if we will see, if in your example, if in your problem, it is given that the feeding distance in steel plates, if there is a provision of chills is given. Okay, so by using the chills, the maximum distance the riser can feed increase to 4.5 T plus 2 inch. Okay, in left part and right part. So I will write at the end. So if we see the bars case, so I have already discussed about the definition of the bars and plates at the starting of this video. So you can so if you see in case of bars, the riser can fill the maximum distance of 6 root T times, where T is the thickness of your bar, to the left part and the right part. Okay, so and after in the distance of 6 root T, the riser contribution is 0.5 T minus 2T, and your edge contribution is 1.5 T minus 2T. Okay, and then if you will see if there is a use of chills is given, if in example, if in your problem it is given you can use chills also. So for in the case of chills, your feeding distance is 6 root T plus T, this one. So this one will be your feeding distance. Okay, the total distance two riser can feed is 12 root T plus 2T, this one. Okay, so this we have covered in case of bars. Now if we move if we see riser necks and breaker cores. So from here you can see this one, riser is the riser is the unwanted portion, and it should be trimmed off after casting, right? Once its purpose is done, it needs to be trimmed off. So the general rule for riser neck design, at least for skin forming alloys, is Mn is equal to 1.1 mc. So once you calculated how you calculated the riser, now you can see from here we need to design the neck also. So as you can see casting is a very complicated process. Firstly you need to design the pouring basin, after that you need to design the riser, after that after riser you need to design the appendages, and after appendages you need to properly design these riser necks and then their breaker cores also, because these without these breaker cores the riser won't be easily trimmed off from your casting, and then it might cause some defects also. So the general rule for riser neck design for this neck, the modulus of this neck should be around 1.1 times your modulus of the casting. Okay, and then for the economical removal of the risers, breaker cores can be used between the riser and the casting. Breaker cores are typically made of bonded sand or fused ceramic material. Okay. And further, by keeping the mass of the breaker core small, the breaker core quickly reaches the temperature of the surrounding metal and does not appreciably affect the solidification of the riser. So from here, these are the formula of your breaker core. So Ln, this maximum, this distance, this part, this maximum of d by 2. This is Ln is maximum of d by 2, and then your Dn is equal to 1.2 times Ln plus 0.1 d. So from here you can calculate the diameter and length of your breaker neck. And now if you will see if you will see this case. So if your riser is top riser, in previously the riser was side riser, here the riser is top riser. So in the case of like top riser, your Ln maximum is of d by 2, and while Dn is the sum of Ln plus 0.2 d. These are all the like empirical formulas you can say, and majorly in exam they are not asked, but if they are asked, the values will be given. But you need to have the idea like how a casting is designed, like how the parts are designed. That's why I have introduced this. Okay, so like from here, like you can see Ln is the maximum of d by 2, and Dn is Ln plus 0.2 d for side riser of plate casting, and these are the different ratios of Ln, Wn, and Hn. Okay, then if anyone wants to discuss or have any doubt till now, we will discuss. After that, we will move to another section. Anyone who has any doubt till now? There is also one thing I don't know if it is covered in the theory part. So, so while designing your riser, like there is a provision of insulator or exothermic pads also. So if you say like this is your riser, and it is filling, it is feeding some cavity. From here, like some molten mold is coming, and here this one is your chill. This one is your chill part, chills. Okay, and then here at this part your insulation is provided sometimes. Okay, so this is your insulating riser sleeve. the Sometimes like these properties of these chills may be given to you, and then again you need to consider those also for the proper riser designing. Riser designing. So previously, you find that the riser design, as you go move ahead, like the design becomes more and more complex. So previously it was only like four methods we like discussed, and then after that four methods appendages came. After appendages riser designing came. After riser designing number of risers came. And after number of risers like chills and these heating pads came. So the problem becomes more and more problem. So this is a I want to like tell you this is what happens in a real life. So it is not a easy process to optimize your casting. So in casting also it is not possible that all of your sections have uniform thickness. Generally we don't achieve in the normal casting process. So in the advanced casting processes it is possible to have a uniform thickness. Okay. So so if you have any doubts, feel free to ask. Meanwhile, meanwhile I will see like what we will discuss now. So so I was discussing this also okay, this was in this okay. So I was discussing this also so if you're if the maximum feeding distance in your section is exceeded, the edge will give a sound edge to its usual L. Okay. But centerline shrinkage may extend for some variation in distance into the area that would ordinarily be expected to sound cause of the riser effect. Okay. So there is one more thing. So in short, I will write the formulas for you. So for bar, what we discussed, we are not doing problems on this how much feeding distance or if you're using chills and all, what will be feeding distance. You can do it you need to remember the formula. So for bar, the feeding distance is 6 root times t, and for with the uses of chill, this will be around 6 root t times plus t. Okay. So this will and then for plate your feeding distance will be 4.5 t. And by using chills, if we will be using chills, then this will be 4.5 t plus 2 inches. These are the general conventional formula. And another thing is the distance between risers can be dramatically increased. By that we can reduce the number of risers needed to ensure a sound casting. Okay, if we place a chill, so if a chill is placed between risers in a casting section where there is no natural cooling edge, it can be used to establish an artificial end effect. Okay, so this I wanted to cover, and riser neck discuss briefly in this. Okay, so yeah, riser neck I have discussed. And there is one more term which is known as the feeding aids. These are provided to feed for longer time. Okay, so this is also the and then this is how this is different from the riser. So a riser liquid remains in liquid for longer time also, but here it is used for keeping riser in liquid for more time. This feeding aids. Okay, so I will just briefly introduce this term, and then so there is term called So this is your feeding aids. So these are use and then the use of the exothermic material and insulators. Example, graphite or charcoal powder, rice hulls, mixture of iron oxide and aluminum powder is generally used in the feeding aids. This will effectively reduce the size of the riser as it will be like like a larger time. Okay then, so I wanted to introduce this term. Mm, okay then, what should we do then? And then also like the advantages of these feeding nets are that they delay solidification and the formation of the skin of solid metal in the riser, which promotes atmospheric puncture of the riser and which assist in the transfer of metal from the riser to the casting. Then the alloys, specifically those that have a wide freezing range, benefit the most from feeding it. Okay, and then increases the temperature gradient between riser and casting. As a result, direct solidification from casting to riser is promoted. The stronger feeding path is established. And further, by reducing the rate of heat transfer between the riser and the mold, there is an increase in the effective modulus of the riser when compared with the geometric modulus of that of the riser. Okay, so this was the thing, and then okay, then let's do one or two problems on the feeding distance. Okay, so if you see, there is a plate. This has a distance of 35. This has a distance of 25, and then the thickness is of 10. So, so the problem will be what will be the feeding distance and what will be the number of risers needed. So, firstly, we need to carefully see like where to put the riser. Okay. So the riser is put at a distance where it can feed the largest distance, largest farthest location. Okay. So for here, if you put a top riser, we will put it at the center here. If it is a top riser, and then here, for the top riser, we have already calculated the feeding distance is 4.5 of the thickness time. So from here, we can see that the thickness here is 10. So it can feed around 45 centimeter, and our farthest is like 35 and 25, and it placed at center. So this will easily feed. Okay. And this was is this can be made little bit of complicated. Now if we see like one more problem, so if there is a this has like dimension of 100 by 40 by 40. Okay, this is a case of bar, from directly you can see. Now if you will calculate the feeding distance for, so feeding distance is 6 root times t, right? And here the thickness is 40. So sorry. Okay, so from here if you will see, the feeding distance will come around 38 centimeter. So this is a feeding distance. So you need to as it will be feeding 38 distance only. So you need to put two risers. So if anyone asks you in exam what is the number of risers needed, you can calculate the feeding distance and then you can see the ratio will be. So what? So one riser can feed up to 38 centimeter distance only. So you need to put two risers here. So this problem will need two risers, and for the case of side riser, for the top riser, for the side riser you can think what will be the case, and then if there is a if chill is also provided, like suppose if someone said I will provide chill, then what will be the number of riser? It will be 1 or 2. So for the chills case, the feeding distance is 6 root t plus t. So your 6 root t is 38, we have already calculated, and your thickness is 40. So this will come around 78 centimeter. Okay, so as you can see, like so it will can feed around 78 centimeter only. So and your but you need to feed your cast till 100 centimeter. So definitely you need two risers. In one riser, this problem can't be like done. So you need two risers. Okay then. I hope this is clear. If you have any doubts, mean you keep on asking, else it will be a problem then. So, okay, then we will move to the last section of the today's part. Then we will wrap up. Okay, then we'll briefly discuss about the special casting methods or some of the casting methods. So, firstly, like different casting technology, like so if you can see, like so if you can see like the casting techniques, so it can be classified into expandable mold or temporary mold casting. So yeah, like so it is two types, like expandable mold, permanent mold, or continuous casting. Basically the casting techniques are of three types. So this expandable mold, uh, in the expandable mold there are like sand molding, cell molding, investment casting, full molding, and CO2 molding are comes. Okay, so if I will write it as like so first one is the sand molding, second one is the cell molding, third one is the investment casting. The fourth one is your like full molding, and then your CO2 molding comes. The brief like complete discussion has already been done in the theoretical parts. You can go through this. I am just revisiting them for your revision purpose only. So these are your expandable mold or temporary mold. Now if you will go to the type of the permanent mold, so you can see like permanent mold are like the centrifugal, another is the die casting, and then the third one is your slush casting, and then fourth another is squeeze casting. And then finally the continuous casting comes. So because each one has like already been discussed in detail in your in the last week's tutorial for the other TA, which happened on Monday, and also by the Professor Jha. That's why I'm not discussing them in depth. But if you will see like briefly the cell molding, these are generally used for making coarse or internal surface and smooth and rigid. And these are generally हाँ सर वो बस खत्म हो गया सर मैं लास्ट बार उसको रीड कर रहा हूँ और अभी प्रिंट करके भी आपको दूंगा सर 15-20 मिनट में हाँ सर अभी अच्छे से दिखा है सर वो मतलब उसके अंदर मतलब वो ऐड किया है सर और वो फिगर और सब चेंज किया हाँ हाँ So I think some network issues. What is it? Okay, so we were discussing about these expandable mold or and then the permanent mold. So another thing is the investment casting, which is also called as lost wax casting or precision casting. So and here the maximum casting weight is less than or equal to 10 kg. For this one is generally for lightweight only. And here the pattern is of wax. And then if we see about the slurry, so slurry is generally of ethylene silicate and silica fluor or water. And here the vacuum is used to reduce the gas defect, and it is a costly setup. Okay, and then the applications are complex shapes, high melting point and strength, and then the turbine blades. It is used for turbine blades, and then no machining required for jet engine parts, complicated and expensive medical implants, gold ornaments, denture. Okay, so these are the generally the casting parts, and then if we move to the CO2 molding, then Na2SiO3 is around 2 to 6% is mixed with the sand. Then if we see the reaction of Na2SiO3 with CO2, it gives around SiO2 and Na2CO3. And for 1 kg Na2SiO3, like 0.6 to 0.7 kg of CO2 is needed, and it is used when strength is required in molding sand in large casting. And then if we move to the centrifugal casting, so it is also called as liquid forging, and then it is of three types. First one is true centrifugal, another is semi-centrifugal, and then the last type is the centrifuging type. So true centrifugal is used for the hollow cylindrical pipes, gun barrels, cylindrical liners. These all these applications have already been done by the Professor Zaha's lectures. Just revising them. And then if you see about the die casting, it has advantages like it provides complex shapes within closed tolerance. Okay, then I think as they are generally already been discussed by the previous TA and uh, by the Professor Jha also. So what we can do if if anyone has any doubt, we can discuss now, or else we will wrap up, because what I wanted to cover the concept of appendages I have already done in the today's lecture. So if anyone has any doubt or any issues, please feel free, or else we will wrap up.
Yeah, Rahul, this is Shiva.
Yeah, please, yeah,
I am audible.
yeah, you're audible.
Hmm. Yeah, Rahul, in week six assignment, the question number two is wrongly evaluated. So, couple of posted also something like in the ask a question.
Okay.
Many of guys are raised the question actually, but we didn't get any feedback on that actually.
Okay, so you dropped the mail or something? Like
Yes, yes, yes.
okay. So I think by the end of this week, or in the working next Monday or Tuesday, they may correct this, or we will evaluate it correctly. Okay.
Okay. Okay.
Okay. If anyone have other questions or issues, please feel free, or else.